Hello, this is Kent Mayhew, and we're at New Thermodynamics. We're going to be talking about Avogadro's hypothesis and its limitations. So traditional thermodynamics is all based upon intermolecular collisions being elastic, and this is wrong. It's a no-no. It's a super ball analogy. The traditional assertion is that intermolecular collisions are elastic, hence they obey the following relation. Okay, mass 1 versus mass 2 in terms of the velocities. Consider a gas molecule striking a wall. Beyond the question as to what its real mass is, the awkwardness goes beyond this. I mean, there's no real mechanism for both the wall and the gas molecules to be related to kT over 2, as is given in traditional kinetic theory. Okay, furthermore, the notion that gas molecules being balls is superficial at best. So now let's consider kinetic theory, but based on inelastic collisions. Okay, so the walls act as massive immovable objects. Okay, and therefore the gas molecule does not simply bounce off the wall. Rather, the vibrating walls imposes a mean kinetic energy of kT over 2 directed along the x-axis onto each gas molecule, and temperature being T and Boltzmann's constant being K. Okay. Now, the walls therefore act as an engine, continually exchanging, pumping, imposing, however you want to look at it, a mean kinetic energy of kT over 2 along each axis that is perpendicular to the wall. Okay, so the net result being that each gas molecule will possess a mean kinetic energy of 3 kT over 2, that being the rotational plus translational energy. Okay. So on the previous slide, we now understand why traditional kinetic theory of gases has certain validity, although it was far from correct. Okay, and the reason again was the walls impose the kinetic energy onto the gas molecules. It should be stated that in my theory, both the translational and rotational energy come from the wall's vibrational energy. Okay. Now, this is different than traditional kinetic theory, which is based on equipetition. Now, the concept that different gases in thermal equilibrium will exert the same pressure while possessing the same mean kinetic energy per unit volume is illogical at best. Think about it. How can you have the same pressure if you have different masses of molecules and if they have the same mean kinetic energy? It doesn't make sense. Okay? Moreover, when a gas molecule collides with another gas molecule, then it adheres to the conservation of momentum, i.e., in terms of the final and initial velocities, we can write this. In order to understand inelastic collisions, we have to realize that when gaseous molecules collide, then heat, whether you think of it as radiation, photons, or phonons, are given off. Hence, although such collisions are inelastic, the energy remains conserved. Okay? And when such inelastic collisions occur within a closed system, then the other gas molecules and or surrounding wall molecules should absorb any collision-derived heat that is given off. Now, in other videos, I discussed that I'm not sure whether the photons within a enclosed system is due to the blackbody radiation or due to the heat and the inelastic collisions, right? So there's going to be a combination. So you'll see me in various videos saying blackbody / thermal radiation. Okay. Accordingly, such collisions generate heat becomes part of the equilibrium state between molecular collisions and vibrations, plus the emission and absorption of radiation. Okay. So we've got to now consider that the heat given off is part of the thermal equilibrium within a system. Okay, so now let's move on to the pressure-temperature relationship. Okay, the idea of inelastic collisions help formulate an explanation for both viscous dissipation and natural pressure-temperature relations. Okay, and that meaning that as the pressure goes up, temperature tends to go up. Okay, and this is based upon molecular collisions are generally inelastic. Therefore, heat is given off. So you can imagine that as the pressure goes up, then the energy involved in each collision either goes up or the number of collisions go up. Either which way, this is going to require or result in the heating of the system. Okay, So the implication being that intermolecular collisions, even in condensed matter, may be elastic. Again, this is in agreement with what is witnessed, like consider the Earth. As you go down deeper, the pressure increases, so does the temperature. So there's both a natural pressure-temperature relationship. And again, it's molecular viscous dissipation. Okay? So now it should be stated that it has also been determined that collisions between photons and electrons are inelastic. So if photons and electrons have inelastic collisions, why would anyone even consider that intermolecular collisions are anything but inelastic? Okay, so Avogadro's hypothesis is limited to sufficiently dilute gases, and this is where the main interaction is gases colliding with walls. Okay, so herein the walls impose their kinetic energy onto the gas. In high-density gases, the mean free path becomes too small, so Avogadro's hypothesis does not hold. And this is because the majority of the collisions are between the gas molecules, not between the gas molecule and walls. Okay? Equally, this happens when a gas has no walls. We'll expect Avogadro's hypothesis to falter. In such situation, the gas molecules are most likely to collide with each other, right? Hence, they do not adhere to kinetic theory. Accordingly, kinetic theory, the ideal gas law, Maxwell's velocity distributions, and Avogadro's hypothesis all begin to falter when the majority of the collisions are between gas molecules. This happens in high-density gases and in situations where the gas has no walls. We should also discuss that Avogadro's hypothesis, and equally equipartition theory, falters at low temperatures. Okay, so as temperatures approach absolute zero, it is accepted that both falter. The current explanation is based upon quantum arguments, and this leaves open the plausibility of a complication of our simple reality. Okay, a simple argument that I believe is that the fact that the thermal radiation density is no longer proportional or directly proportional to temperature as temperatures drop. Okay, and basically we start to see this around 250 degrees K, and it becomes really apparent below 100 degrees K. Now, if you want, I discuss this in my video latent heat and its probability. Okay, so you can get a better understanding by going and visiting that video. So I have a book out, New Thermodynamics, A Note on Entropy, which talks about this in more detail. I'm also rewriting the book for the third time. I'm going to rename it New Thermodynamics, Goodbye to the Second Law. The reason is I had new realizations, and so I had to rewrite chapters 4 and a few other chapters. Okay, now all the chapters that were rewritten can be found on my website, www.newthermodynamics.com. Most of what is discussed on these videos are in my books, papers, and can be found on my website. Now, it's hard for me because I'm alone at this, so I apologize for my odd mistake, which certainly exists, and as always, I'm really apologizing for being human. Okay, now, people, please help. 2 brains are better than 1. Okay, accordingly, any help and improvement is always appreciated. Okay, I am far from perfect.